Hello, welcome to lesson 13 of the Practical OSPF series. In this lesson, we're going to talk our way through the OSPF network types. Before we begin, I'll quickly mention that I'm really excited to get to this lesson. You see, the OSPF network types is something that confused me for years when I was first trying to understand OSPF. I kept finding incomplete descriptions or write-ups trying to explain it, but the concepts never fully clicked for me. While trying to learn, I kept telling myself, there must be an easier way to explain the OSPF network types. And I'm happy to say I think I found that way. But I'm curious, is this something the rest of you have struggled with as well? Let me know if this is a concept you've tried to learn before and found confusion with. And then, when the video ends, let me know what you think of this way of explaining it. With that said, let's get into our lesson. There are 5 different OSPF network types that exist, and they all kind of fall in these 3 categories. The first 2 is actually something you should be pretty familiar with, because it's the 2 network types that we've already been using throughout this course. That is point-to-point networks and broadcast networks, and this is what they look like. Point-to-point networks involve any sort of network topology that involves one router directly connected to another router. If you're using serial interfaces, that's going to default to an OSPF point-to-point network type. The idea there is that since serial, by definition, can only support 2 hosts, one side of the wire and the other side of the wire, with OSPF, we know that a serial link isn't going to connect a bunch of other clients. Therefore, serial links typically are one router directly connected to another. That's why OSPF defaults to point-to-point network type. Now, serial links are pretty rare in the modern networking age. Most of the time, routers directly connected to each other are using Ethernet, or potentially fiber, and you would manually set that link in OSPF's configuration as a point-to-point network. One way or another, when OSPF is thinking of a point-to-point network, that is a type of network that only supports 2 routers. By comparison, broadcast networks are a multi-access network that can support any number of routers. If you're using Ethernet networks, that's going to default to a broadcast type of network. The idea there is Ethernet is multiple access, and therefore you don't know whether there are other routers on that link. There could be. So OSPF plays it safe and always assume that any Ethernet link is a broadcast network type, whether there are or are not other routers on that link. So that's the first 2 OSPF network types, and this is what they look like. The third OSPF network type looks like this, and is referred to as a point-to-multipoint network. This is the type of network you would use in hub-and-spoke type deployments. Meaning, if you had a network topology where one router, the hub, could see all the other routers, but all the other routers, the spokes, can only see the hub, that is what you would call hub-and-spoke, and that's where you would use point-to-multipoint networks. By comparison, both of these 2 network types support full mesh connectivity, which is to say, every router on the link can speak to every other router on the link. In the case of broadcast, router 2 can speak to every router on the link, just like router 1 can speak to every router on the link, just like router 4 can speak to every router on the link. In the case of point-to-point, you'll notice that I put full mesh connectivity in quotes, since possibly that term is a little bit overkill, since point-to-point will only ever have 2 networks on that link. Either way, it does satisfy the definition of full mesh, meaning that every router on the link can speak to every other router on that link. You don't have that in point-to-multipoint segments. With point-to-multipoint segments, the physical network topology is actually preventing the spokes from reaching each other. The only connectivity is going to be from hub to spoke and back. Now, an important thing to keep in mind about these OSPF network types is that each of these layouts involves a single IP network, which means all 4 of the routers in this broadcast network exist within a single IP subnet. Just like this would be a single IP subnet, and this right here would also be a single IP subnet. If the connectivity in this point-to-multipoint segment actually looked like this, where you had 3 different IP subnets, then what you would actually have is 3 point-to-point networks. You wouldn't actually have the point-to-multipoint that we just discussed. With true point-to-multipoint, these all belong to the same IP subnet. That's what makes them different from 3 different point-to-point links. Now, you might be thinking to yourself, point-to-point makes sense, it's just 2 routers connected to each other. Broadcast makes sense, it's just a bunch of routers connected to an Ethernet switch. But what kind of network topology is going to allow for this hub-and-spoke connectivity? Well, the answer to that question is that this type of connectivity isn't something you would see within your LAN. Instead, these OSPF network types have more to do with WAN connectivity. Consider this point-to-point network. It isn't a single router plugged in directly to another router. It's some sort of WAN connectivity that makes it look like one router on one side of the internet is connected to another router. Potentially, these are two edge routers connecting two different sites together, and you're paying some ISP for some sort of connectivity that makes it look like your routers are directly connected to each other. This would be something like leased lines or something like pseudo-wires or L2 VPNs. With broadcast networks, you have multiple different sites all connected using some sort of WAN technology via some ISP, but the main point is that with this WAN technology, you do have full mesh connectivity, which means all these routers can all speak to each other. With point-to-multipoint, you're still using some sort of WAN solution, but they're deployed in some sort of hub and spoke topology, something like DMVPN, for example. One way or another, what you have to remember is that whatever WAN technology you're using, if it makes it look like you have two routers directly connected to each other, you have a point-to-point WAN. And if it makes it look like you have a bunch of routers that all have full mesh connectivity to each other, you have a broadcast OSPF network type WAN. And if you're doing something like a hub and spoke, then you're using point-to-multipoint networks. That's where these OSPF network types mostly come into play. It's more to do with the WAN than the LAN. So that takes care of telling you about the three different OSPF network types. But what about these two over here? Well, these two are nothing but these two, except with some sort of WAN technology that doesn't support broadcast or multicast packets. In the case of a full mesh connectivity that doesn't support multicast or broadcast, you would have what OSPF calls an NBMA network, or a non-broadcast multi-access network. And in the case of a hub and spoke connectivity that doesn't support multicast or broadcast packets, you would have a point-to-multipoint non-broadcast network. And again, these two are really the same as these two, except that they don't support multicast packets. Therefore, OSPF has to tweak the way it operates, but we'll get into the specific differences in a moment. Either way, that's the rundown on the 5 different OSPF network types. And remember that they all follow these 3 network layouts. Now, what we're about to do next is talk about more of the differences between all 5 of the OSPF network types. And to do that, we're going to continue using this topology images. But we're going to do this in a different way that I've seen it done before. You see, normally what I see happen is someone introduces point-to-point and then gives you a bunch of information about point-to-point network types. And then someone introduces broadcast and then gives you a bunch of information. And then NBMA and then a bunch of information, and then so on and so forth with a bunch of information after each. What I've found though is doing it that way makes you sort of forget what happens in previous network types, which makes it hard to really understand how they all tie together. So instead, we are actually going to talk about all 5 network types at the same time. But we're going to do it across the dimension of the various differences between each network type. Meaning, I'm going to give you a difference and I'm going to show you how it applies to all the 5 network types. And to do that, I've created this fun little table. And already, 2 entries in this table have already been revealed, outlining the things that we've already discussed. Remember, we said that point-to-point networks have a maximum of 2 networks on the link, whereas there is no maximum for all the other 4 network types. Moreover, full mesh connectivity is assumed with all of the network types except our point-to-multipoint network types. Again, every router in either of these topologies can speak to every other router on the link, whereas hub and spoke, by definition, spokes can only speak to the hub, and the hub can speak to all the spokes, but the spokes can't speak to each other. So we're going to use this format to continue talking about the OSPF network types. So continuing, after the first 2 major differences of the OSPF network types, we have this 3rd major difference, and that has to do with which of these network types require a designated router. And the answer is only these right here. That's the only network types that require a designated router. Remember, we talked about the designated router back in lesson 6. We told you that the purpose of the designated router was to streamline the router advertisements on a multi-access link. The idea there is if router 2 had an update to send to that link, it's going to send it to everybody on the link, but if everybody receives that update, they might then try and send the exact same update to everybody in the link again and again. That's where the DR comes into place. The DR is a single router which is going to streamline all the network updates on the multi-access link. What will happen is if router 2 has an update, it'll simply update the DR, and the DR will be responsible for updating the other routers on the link. Now looking at the topology, you can kind of tell why you might want a DR on multi-access full mesh network types. But what about this point-to-point? Well, if you think about it, the only time router 1 is going to put something on the wire is for router 2, and same thing in the other direction. So on a point-to-point network, you don't really need to bother yourself with a designated router. But what about point-to-multipoint? those are actually multi-access network. Remember, there is no limit on how many routers you can have. It's whatever your WAN technology will support. But recall that the spokes don't see each other. From the perspective of each spoke, there's only one other person on the link. It's only the hub. The hub is the only router that can actually see the other spokes. So naturally, it's going to sort of do the job of the DR inadvertently. So we don't need a formal designated router on point-to-multipoint and point-to-multipoint non-broadcast network types. Therefore, the only place you'll see a designated router is on broadcast or non-broadcast multi-access networks. Which brings us to the fourth difference that we're going to outline with OSPF network types, and that is a simple memorization exercise, that is the default Cisco hello and dead timers. Now, if you're studying for a certification exam, you'll probably want to commit these to memory. If you're just learning OSPF to use at your work, understand that most of the time you're probably going to be setting default hello and dead interval timers. One way or another, the way I like to remember this is that these normal, more common network types, point-to-point and broadcast, use the faster default hello and dead interval timers of 10 seconds and 40 seconds respectively, and all these other weird ones use this higher one of 30 seconds of 120 seconds. So that's just another small difference between the different OSPF network types. This next difference, however, is a little bit more significant. The fifth difference that we're going to talk about has to do with which of these network types support automatic neighbor discovery. And you'll see that all of them do except the ones that don't support multicast or broadcast packets. And that sort of makes sense because the basic way that OSPF discovers neighbors automatically is using multicast packets, specifically a hello packet addressed to a multicast address. In the case of point-to-point, if router 1 is trying to discover router 2, router 1 is simply going to put on the wire a hello packet addressed to 224.0.0.5. That'll make it so that router 2 will receive it and then can respond, and then router 1 and router 2 can continue the neighbor adjacency process to become neighbors with one another. In the case of broadcast networks, it's the same thing. If router 2 newly joins this link, it's going to send out a hello packet, destination address 224.0.0.5. That's going to get to all the other routers on the link, and then they'll all respond in order to become neighbors with the new router that just joined the link. With point-to-multipoint, it works the same way. Whether the hub sends the initial hello, or the spokes send the initial hello to the hub, one way or another, since they can use this 224.0.0.5 address, they can automatically determine what other routers are on the other side of that link. But how does neighbor discovery work on network types that don't support multicast or broadcast packets? Well, in those cases, you have to manually configure a neighbor's IP address. For example, if this was an NBMA network type and router 2 just joined the network, and I wanted router 2 to become neighbors with router 4, I would have to jump onto router 2 and manually configure router 4's IP address. That would prompt router 2 to send a unicast hello packet to router 4 in order to try and become neighbors with router 4. Upon receiving it, router 4 would respond, and then they would continue the neighbor adjacency process. Same thing with the point-to-multipoint non-broadcast segments. Now, the thing to understand though is that that manual neighbor IP address configuration is only required on one side. Meaning, if I jump on router 2 and manually configure the IP address of router 1, router 2 will send a unicast packet to router 1. But router 1 will look at that packet and see the source IP address to learn router 2's IP address. And then router 1 can simply send a reply to continue the neighbor adjacency process. So the manual configuration of IP addresses only really needs to happen on one side. Okay, so that takes care of the initial discovery of the neighbors, but how does continued communication work in the rest of the neighbor adjacency process? Well, you'll notice in all cases, continued communication happens via unicast packets, with one exception, and that is point-to-point networks. On a point-to-point network, it doesn't really matter the destination IP address you put on the packet. Either way, whatever router 1 sends via OSPF is meant to go to router 2, and whatever router 2 sends via OSPF is meant to go to router 1. So they can continue to use this multicast address without really any downside. But on these multi-access segments, if router 4 is trying to continue the neighbor adjacency process with router 2, if router 4 is using the multicast address 224.0.0.5, that neighbor adjacency communication is actually going to be bothering all the other OSPF routers on that link. Therefore, on multi-access segments, that is both broadcast and point-to-multipoint segments, continued neighbor communication is sent unicast directly to your neighbor's IP address. Okay, so that takes care of the rest of the neighbor adjacency process, but what happens after that? how are the routers on each of these network types going to send LSAs to each other if a routing update has just occurred? Well, what you'll see is that point-to-point links will continue to use the same multicast address that they have been using. Once again, there's no reason not to. One way or another, anything OSPF sends on this link is only meant to go to the peer, so they can simply continue to use this address without any problem. In the case of point-to-multipoint and point-to-multipoint non-broadcast, they will again continue to use unicast packets just like they did for the rest of the neighbor communication in the neighbor adjacency process. But what's happening over here? Well, remember that with broadcast and NBMA network types, a designated router is elected. So we can't just have all the routers on those networks simply unicast updates to each other. Instead, they have to follow the rules of the designated router by sending updates through the DR. Now, back in lesson 6, we talked through all the intricacies of how that works. We showed you how the DR and the druthers in the BDR use the multicast addresses 224.00.5 and 224.00.6 to send updates on a multi-access segment. Everything we talked about back in lesson 6 is exactly what would go on a broadcast network type. So if you want a refresher, I'd refer you back to that lesson. In the case of NBMA, however, a non-broadcast link cannot use the multicast addresses 224.00.5 and 00.6. Therefore, instead, they're going to replicate the exact same sequence that occurred on a broadcast segment, but they're going to do it with unicast packets. Meaning, if router 2 has an update to send on this link, it's going to unicast something to router 1, and when router 1 gets it, it's going to unicast that update to router 3 and router 4. It's not going to be able to use something like 224.00.5 to punt it out to all routers in a link at the same time. So the process is still the same as what we talked through back in lesson 6, except on NBMA networks, it's done via unicast packets. And so this finally brings us to the last major difference we're going to talk about. And if I'm honest, I think this is probably the most significant. This is the one that sort of lands the plane on why all these different OSPF network types even matters. And it's fundamental to the root purpose of OSPF. So remember that OSPF is a routing protocol, which means its entire purpose is for routers to share routes with one another so that they can forward data packets to each other in a smart and efficient way. This last entry has to do with what next hop IP address is used in the routing table entries for all the routes learned on either of these network types. And we're going to start by talking about point-to-point. What happens is if router 2 shares an update with router 1, when router 1 is installing that route into its routing table, it's going to use a next hop IP address of its peer, in this case router 2. That is how data packets will be forwarded across this link and onto the other side of router 2's network. But what about on these broadcast segments? Remember that initially router 2 had the update to send to this link, but that update was sent via the DR. So what is the next hop IP address that router 4 is going to use in that route that it just learned from the update it learned via router 1, which was originated from router 2? Well, remember that these network types do support full mesh. So router 4 can absolutely speak directly to router 2. Therefore, even though the routing update might have been learned via the DR is uninvolved in actual data packet forwarding. Router 4 will use as the next hop IP address the originating router in the route, in this case router 2. So if router 4 has a data packet that it needs to send to a network on the other side of router 2, it's simply going to use router 2 as the next hop IP address. The DR is only involved in streamlining route advertisements. It's not actually involved in the middle of all data packet forwarding. Which brings us to the point-to-multipoint network types. Remember that if router 2 sent out an update, since router 2 only sees the hub on this particular network, the hub is going to be in charge of forwarding that routing update to the other spokes on that link. So now we have a conundrum. What should router 4 use as the next hop IP address? Now you might think it could be easy for them to also use the originating router, but remember, we don't have full mesh connectivity on point-to-multipoint segments. So if router 4 used router 2 as the next hop IP address, that communication would never actually flow to router 2. Instead, on point-to-multipoint network types, the hub is always used as the next hop IP address. Router 4 would use the hub as the next hop IP address, and the hub would then be in charge of passing that on to the other spoke. Now, I'll also quickly say that that route update that router 2 sent, when router 1 installs it into its routing table, router 1 will indeed use the spoke as the next hop IP address. But when that update is forwarded to the other spokes, these spokes will use the hub as the next hop IP address for data packets. That, in my opinion, is probably the most significant difference between point-to-multipoint network types and broadcast network types. So keep that in mind because it actually relates to the ultimate goal of OSPF and any routing protocol, and that's forwarding data packets. And that wraps up all the differences I wanted to illustrate for you regarding the 5 different OSPF network types. The main takeaways from this lesson is understanding the different network types and all the things we just went through in this table. From a practical perspective, remember that 99% of the time you're just going to be configuring point-to-point and broadcast network types within an OSPF LAN. The other network types really only come into play when you're doing OSPF across a WAN. And instead of trying to memorize everything, just use this table as a reference to identify what type of network you should use. For instance, does your WAN topology support full mesh and multiple routers? If so, one of the broadcast network types is what you want. Does your WAN topology support sending packets to multicast addresses? If so, broadcast is the right network type to use. If not, NBMA is what you're looking for. So feel free to take a screenshot and use this table as a reference. And if you want to share that screenshot publicly, go for it, but please give credit to where you got it from. Either way, that brings this lesson to a close. As always, if you learned something and appreciate the effort that went into creating this lesson, then do me a favor, help me out with the YouTube algorithm by liking, commenting, and subscribing. And of course, the best way to say thanks is by sharing this video publicly. Either way, thank you for watching this video, and we'll see you in the next one.